Welcome to Easy BTech. Today we have to discuss types of matrices and properties. First, we have to discuss some of the important types of matrices. First one is transpose of a matrix. Transpose of a matrix. A matrix obtained by any given matrix capital A by interchanging rows into corresponding columns or columns into corresponding rows is called transpose of capital A. It is denoted by A transpose. A matrix obtained by any given matrix capital A by interchanging rows into columns or columns into corresponding rows is called transpose of capital A. It is denoted by A transpose. So there is a one more representation is also there. What is that? Suppose for example, if capital A equals to Aij, then the transpose of capital A is denoted by A transpose that equals to, this is the another matrix Bji, where this Bji equals equals to Aij. That means here Aij, that means ith row and jth column is transferred into jth column and jth row and ith column. That means here the rows converted into columns or columns converted into rows. So it is the one more representation. Here some of the properties of the transpose of a matrix. Properties of transpose of a matrix. What are the properties here? We can see what are the properties. The property 1 is A transpose whole transpose equals to A. The second one, A plus or minus B whole transpose equals to A transpose plus or minus B transpose. Come to the third one, some constant K into A whole transpose can be written as K times of A transpose. That means K into A transpose. The property fourth one is AB whole transpose is equals to B transpose into A transpose. These are the very important properties. Once again, just repeat what is the definition and what are the properties. A matrix obtained by any given matrix capital A by interchanging rows into corresponding columns or columns into corresponding rows is called transpose of capital A. It is denoted by A transpose or A power T. We can read as A transpose. So one more representation, if capital A equals to A small aij, that means it represents small aij is an element in ith row and jth column. Then the transpose of this matrix capital A is A transpose equals to Bij or Bji, where Bji equals to Aij. That means Aij is a element in the matrix capital A. It is occupied at ith row and jth column. The same element occupied in the A transpose is jth column and jth row and ith column. This is the meaning of Bji equals to Aij. What are the properties of transpose of a matrix? The first property is A transpose whole transpose equals to capital A. Second one, A plus B whole transpose equals to A transpose plus or minus B transpose. Constant into A whole transpose equals to K times of A transpose. AB whole transpose equals to B transpose into A transpose. See an example on this topic. Example. A equals to 1, 2, 3, 0, minus 1, 2. This is the 2 by 3 matrix. It contains 2 rows and 3 columns. Now, A transpose equals to, what is the definition of A transpose? Interchange rows into corresponding columns. That means rows into corresponding columns. So first row converted into first column. So first row is 1, 2, 3. So this 1, 2, 3 first row converted into first column. Come to the second row. Second row is 0, minus 1, 2. This second row converted into second column. Second column is 0, minus 1, 2. So this is the transpose of A. It is denoted by A power T. So here this matrix contains 3 rows and 2 columns. This is the one of the example of A transpose. Now come to the next one, symmetric matrix. The next one is symmetric matrix. Symmetric matrix. What is this symmetric matrix? Already we discussed about the transpose of a matrix. Transpose of a matrix means rows convert into corresponding columns. So in this process, if you convert rows into columns, if the matrix remain unchanged, then the matrix is said to be symmetric matrix. That means suppose for example, a square matrix, see the definition, a square matrix capital A is said to be symmetric if A transpose equals to itself. A transpose equals to A. That means if you transpose a matrix, again if you get the same matrix, A transpose equals to A, then the matrix is said to be symmetric. See an example. A equals to 2, 3, 4, 2, 5, 6, 4, 6, 0. This is the one of the square matrix. It contains 3 rows and 3 columns. If you calculate A transpose means interchange rows into columns. The first row 2, 3, 4. This is the first row. So the transpose means rows convert into columns. 2, 3, 4 first row converted into first column 2, 3, 4. Second row 2, 5, 6. This 2, 5, 6 converted into second column 2, 5, 6. The third column 4, 6, 6. 4, 6, 6. So after converting all the rows into corresponding columns, just observe the first row 2, 3, 4. Here also 2, 3, 4. Here you will get, oh sorry, one small change. This is 3. This is also 2, 3, 4. See the first row 2, 3, 4. The first column is 2, 3, 4. Second row is 3, 5, 6. Second row is 3, 5, 6. Second column is 3, 5, 6. The third row is 4, 6, 6. The third column is 4, 6, 6. If you observe, after interchanging the rows into columns, here we are getting the same matrix capital A. That means A transpose equals to A. That means the transpose of a matrix is itself, then it is called symmetric. Therefore, here A is symmetric. A is symmetric. Once again, I am telling you the definition. A square matrix capital A is said to be symmetric if A transpose equals to A. A transpose equals to A means after interchanging the rows into corresponding columns, again we are getting the same matrix. That is the meaning of A transpose equals to capital A. Come to an example. A equals to 2, 3, 4, 3, 5, 6 and 4, 6, 6. This is the one square matrix. Its order is 3 by 3. It contains 3 rows and 3 columns. Now A transpose means rows convert into corresponding columns. First row 2, 3, 4. First column 2, 3, 4. Second row 3, 5, 6. Second column 3, 5, 6. Third row 4, 6, 6. Third column 4, 6, 6. If you interchange columns, if you interchange rows into columns or columns into rows, again we are getting the same matrix capital A. Therefore, after transposing the matrix, we are getting the same matrix. Then the matrix capital A is said to be symmetric matrix. Now come to the next one, skew symmetric matrix. Skew symmetric matrix. What is this skew symmetric matrix? What is the difference between the symmetric and skew symmetric? Symmetric means A transpose equals to A. Symmetric means A transpose equals to A. Skew symmetric means A transpose equals to minus A. That means additive inverse. So see the definition first. A square matrix capital A is said to be skew symmetric if A transpose equals to minus A. A transpose equals to minus A. That means after interchanging, A transpose means after interchanging rows into corresponding columns, if you get additive inverse of itself. Additive inverse of itself means minus into capital A, minus A. So this is called the additive inverse. So see an example here. Suppose some B equals to, a matrix B equals to 0, minus 1, 3, 1, 0, 4, minus 3, minus 4, 0. This is the one matrix capital B. Here it contains 3 rows and 3 columns. Therefore, this order is 3 by 3. This is the square matrix and its order is 3 by 3. Now, just calculate B transpose. B transpose means first row converted into first column. What is the first row here? The first row is 0, minus 1, 3. 0, minus 1, 3 can be written as first column. 0, minus 1, 3. The first row converted into first column. Now come to the second row. Second row 1, 0, 4. This 1, 0, 4, second row converted into second column. 1, 0, 4. This is the second column. Come to the third row. Third row minus 3, minus 4, 0. This third row converted into third column, -3, -4, 0. So here what happened? We interchanged all the rows into corresponding columns. So after that, if you observe here 0, 0, see the first row 0, 0, compare the first row in the B and B transpose. 0, 0, here -1, but here +1. Here +3, here -3. Here 1, this is -1, 0, 0, 4, but here -4. So 3 here, see the third row, -3, here +3, -4, +4, 0, here this is 0, here this is 0. So what can we observe here? In these two matrices, every corresponding element has opposite sign. If there is a opposite sign, we can take minus common from the each element. Okay, we can take minus common from the each element. So 0, if you take minus from the 0, you will get 0. This is +1, you can write -1. Why? Because minus into minus +1. Again this is -3, if you write +3, minus into +3, again -3. Here -1 can be written as +1. Why? Because minus into +1, -1. This is 0 and come to here -4. Here minus into -4, +4. So here 3, +3 can be written as -3. Minus into, here there is a in front of the matrix we are multiplying with -1. So minus into minus +3. So minus into -4, +4, minus into -4, +4, this is 0. So here I am taking minus common from each element. Why? Because in B and B transpose, each element contains opposite signs. That's why I am taking minus common. If we take minus common from the each element, again we are getting the same element, same matrix capital B. Therefore B transpose equals to -B. So this -B is called the additive inverse of B. So after interchanging the rows into columns, again we are getting additive inverse of itself. That means B transpose equals to -B. Therefore B is called skew symmetric. Skew symmetric. So once again we can observe the example. Once again I will repeat the definition. Skew symmetric matrix. A square matrix capital A is said to be skew symmetric if A transpose equals to -A. See example, B equals to 0, -1, 3, 1, 0, 4, -3, -4, 0. This is the 3 by 3 matrix. After interchanging the rows into columns, we will get B transpose. B transpose equals to, this is the matrix. If you observe the each element in B and B transpose, each element contains the opposite signs. Here see this element, here you can see this is -1 but this is +1. Similarly this is the +3, this is -3. So every element, this is the 1, this is the -1. This is 0, 0. So this is 4, this is -4. So similarly if you observe all the elements are in the opposite signs in B and B transpose. That's why in the B transpose matrix I am taking minus common, then we will get the same matrix B. Therefore B transpose equals to -B. Therefore B is called skew symmetric matrix. Okay, what is the difference between the symmetric and skew symmetric? Symmetric means after transpose the matrix, again you will get the same matrix. But skew symmetric means after transposing the matrix, we will get the additive inverse of itself. That means B transpose equals to -B or A transpose equals to -A. That is the difference between the symmetric and skew symmetric. Now we have to discuss one of the important theorem. Now we can discuss one of the important theorem. See the theorem. This is a very important theorem. What is this theorem here? Every square matrix every square matrix suppose for example that square matrix is some k, can be expressed as the sum of the sum of a symmetric and a skew symmetric matrices in one and only way, that means unique. Once again, see the statement of this theorem. What is this statement of this theorem? Every square matrix capital A can be expressed as the sum of symmetric. Suppose the symmetric matrix I will denote by P. Symmetric, the symmetric matrix is some P, and a skew symmetric matrix, this is I will denote it by some Q. So if you observe here, the sum of a symmetric matrix P and a skew symmetric matrix Q in one and only way, that means it is unique. What is this meaning? So that means, that is, I will tell you, suppose A is a square matrix, then A can be written as P plus Q. That is, if A is a square matrix, then A can be written as P plus Q, where P is symmetric and Q is skew symmetric. Q symmetric. This is the yes. Just observe all of you. If A is square matrix, if A is square matrix, a square matrix capital A, if a square matrix capital A can be written as sum of the symmetric matrix and Q symmetric matrix. This is the our required statement. Now we have to prove this statement. Okay, how to prove this statement? All of you clearly observe. Yeah. Here our statement is every square matrix can be expressed as sum of the symmetric and skew symmetric matrix in one and only way. That means it is unique. So how to prove this one? All of you observe. Proof. See the proof. Let first we have to take a square matrix. Let capital A be a square matrix. Yeah, first we have to take a square matrix capital A. After that we have to prove that A equals to P plus Q, where P is symmetric and Q is skew symmetric. So this A I can write 2A by 2. This matrix capital A can be written as 2A by 2. 2 to cancel, again you will get A. This 2A I can write 2A such that A plus A. A plus A means 2A by 2. This 2 I will write before this sum. This denominator 2 I will write before the sum A plus A. For this sum I have to add and subtract one more matrix, that is A transpose minus A transpose. Here I am adding A transpose matrix and also subtracting the same matrix, remain unchanged. Yeah. Now this can be written as, I will divide this matrix such that 1 by 2 into A plus A transpose plus A minus A transpose. Now I want to multiply this 1 by 2 to this sum and this sum. So then if you multiply with 1 by 2 into A plus A transpose into plus 1 by 2 into A minus A transpose. Here I will denote this 1 by 2 into A plus A transpose, I will write P, I will denote this first matrix by P plus this second matrix I will denote by Q. So this is the A equals to. Therefore, now I will write A equals to P plus Q where P equals to, what is P here? 1 by 2 into A plus A transpose, and Q equals to 1 by 2 into A minus A transpose. Okay, once again see my dear students, I will explain this step once again. According to our theorem, A square matrix, capital A, that means first we have to take a one square matrix. Let A be a square matrix. Capital A can be written as a 2A by 2. 2 to cancel, again you will get capital A. So 2A means A plus A by 2. This denominator 2 I can write 1 by 2 into A plus A. That equals to 1 by 2 into A plus, here I am adding A transpose and subtracting the same matrix. Plus A transpose minus A transpose. Both are cancelled. Again you will get A plus A. So this I will write this one such that A plus A transpose. So I am interchanging these two elements. So first I am writing plus A. After that I am writing minus A transpose. Then after multiplying 1 by 2 to the first sum and second sum, then you will get 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose. Here this 1 by 2 into A plus A transpose I will denote it by P. Here I am denoting this 1 by 2 into A minus A transpose by Q. Then this A can be written as P plus Q, where P means 1 by 2 into A plus A transpose and Q equals to 1 by 2 into A minus A transpose. Okay, that's work. Here we find P and Q. Now we have to show that P is symmetric and Q is Q symmetric. We have to show that P is symmetric. Already in the last slide, already we discussed symmetric means A transpose equals to A. A transpose equals to A, then A is called symmetric. Here we have to show that P is symmetric. P is symmetric means P transpose equals to P. That's why we have to show that. So here show that we have to show that P is symmetric. P is symmetric means P transpose equals to P. Now we have to show P transpose equals to P. So already you know the P equals to, what is P? 1 by 2 into A plus A transpose. This is the P. Now we have to calculate P transpose. P transpose means 1 by 2 into A plus A transpose whole transpose. This is the P transpose. So this can be written as 1 by 2 into A plus A transpose whole transpose. Why? Because here there is a one property, constant into A whole transpose can be written as constant times, that means K times into A transpose. So according to this property here 1 by 2 is the constant. That's why we can write constant into transpose of the remaining matrix. This is that equals to, this is also can be written as 1 by 2 into here A transpose plus A transpose whole transpose. How can we write this one? Why? Because here we have the one more property. A plus B whole transpose can be written as A transpose plus B transpose. By using this property, you can write A plus B whole transpose can be written as A transpose plus A transpose whole transpose. So here this can be written as 1 by 2 into A transpose plus A. Why? Because here I applied one of the property. What is that? A transpose whole transpose equals to A. So at this place of A transpose whole transpose, we can write A. Then just interchange the order of this sum. Then you will get A plus A transpose. 1 by 2 into A plus A transpose means again this is P. So therefore P transpose equals to P. So P transpose equals to P. Then P is called symmetric. Here we proved that P is symmetric. Again, we have to prove that Q is Q symmetric. Now we have to show that we have to show that Q is skew symmetric. Skew symmetric. What is the meaning of skew symmetric? Skew symmetric means transpose of a matrix equals to additive inverse. That means minus into itself. Q transpose equals to minus Q. So now we have to show Q transpose equals to minus Q. Therefore, what is Q? Q equals to, here Q equals to 1 by 2 into A minus A transpose. This is Q. Now we required Q transpose. Q transpose means whole trans 1 by 2 into A minus A transpose whole transpose. So this can be written as 1 by 2 into A minus A transpose whole transpose. Here which property I applied here? Constant into A whole transpose can be written as constant times of A transpose. According to this property, here 1 by 2 is the constant. That's why we can write 1 by 2 into A minus A transpose whole transpose. That equals to 1 by 2 into, here I can write A transpose minus A transpose whole transpose. Which property I applied here? Just see, here I applied a property A transpose whole transpose equals to A. I applied this property here. Now come to the next one. Here, I applied one more property. What is that? See, this is not a right property here. I will show you that here I applied a property A minus B whole transpose. A minus B whole transpose can be written as A transpose minus B transpose. I applied this property here, then you can get 1 by 2 into A transpose minus A transpose whole transpose. This can be written as 1 by 2 into A transpose minus A. That means here I applied A transpose whole transpose equals to A. So now here I am taking minus common from the each term. Here there is a two terms A power T, A transpose. In this A transpose I am taking 1 by 2 common, then you will go minus common, then you can write minus A transpose. Here if you take minus common you will get plus A. That means if you take minus common from the each term, the sign should be changed. Here I am taking minus common from each term, this signs automatically will change. So here this is plus A transpose, it is converted into minus A transpose. Here minus A converted into plus A. Why? Because I am taking minus common from the each term in this expression. Okay, keep this point. If you take common a sign minus in an algebraic expression, every term sign should be changed. So here A transpose converted into minus A transpose, minus A converted into plus A. So this can be written as minus 1 by 2 into, first I will write the plus term. Plus term means capital A. After that I will write the minus term minus A transpose. What is this? In front of there is a minus is there. That equals to minus into this expression is equals to Q. So finally what we proved, Q transpose equals to minus Q. So Q transpose equals to minus Q means this is called, Q is called skew symmetric. Therefore Q is skew symmetric. Therefore Q is skew symmetric. So here what we proved, here we proved A equals to P plus Q, and where P is symmetric and Q is skew symmetric. So here we proved two things. One is A can be written as P plus Q, where P is symmetric and Q is skew symmetric. This is over. Now, but in the theorem, what they asked, this expression is unique. This expression is unique means first we have to, if you take one more expression, then the both expressions should be equal. So see that one. Now we have to show that we have to show that the sum is unique. What is the meaning of the sum is unique? The sum is unique means if you take here sum is unique means what is the sum? A equals to P plus Q. Here A equals to P plus Q is unique. So A equals to P plus Q is unique means if you take one more sum, suppose I will tell you, assume that I am taking one more sum, capital A equals to R plus S, where R is symmetric and S is skew symmetric. So just observe here, already we proved A equals to P plus Q, where P is symmetric and Q is skew symmetric. But we have to prove that this expression, this sum is unique. So when does we say the sum is unique? If we take one more expression, then both are equal, then it is called unique. Therefore, that's why I am taking one more sum, A equals to R plus S, where R is symmetric. Here P is symmetric. If you observe clearly, in this already we proved P is symmetric and Q is skew symmetric. But here also we are taking one more expression, A equals to R plus S, R is symmetric and S is skew symmetric. Therefore, now I will prove R equals to P and S equals to Q. So, how to prove this one? See, A equals to what is A? A equals to R plus S. In this R plus S, what is R? R is symmetric. R is symmetric. What is the meaning of R is symmetric? R is symmetric means R transpose, again you will get the same matrix R. But what is S? S is skew symmetric. S is skew symmetric. R is skew symmetric means, S is skew symmetric means S transpose equals to minus S. Why? Because this is skew symmetric means S transpose equals to minus S. Now I am taking here I am taking A transpose. What is A transpose? First we take A. What is A? Here A equals to, just see, A equals to what is A? R plus S. Then now I required A transpose. A transpose means apply transpose on both sides, R plus S whole transpose. Already I told to you R plus S whole transpose can be written as R transpose plus S transpose. Why? Because here the property is A plus B whole transpose can be written as A transpose plus B transpose. According to this property, we can write R transpose plus S transpose. That equals to R transpose. What the R transpose means? R transpose means R is symmetric. Therefore, R transpose means R plus S transpose. S transpose means S is skew symmetric. Skew symmetric means S transpose equals to minus S. Therefore, this can be written as R minus S. Plus into minus minus. Therefore, this is A transpose. Already you know the A means here. A means R plus S. A transpose means R minus S. Now P. What is P? Already you know P. P equals to 1 by 2 into A plus A transpose. This is P, already we proved. Therefore, this can be written as 1 by 2 into A. A means here R plus S. Here A means R plus S. R plus S. This is A. Plus A transpose. A transpose means already we proved R minus S. Here, if you observe S and minus S both are cancelled, then finally you will get 1 by 2 into 2R. 2 cancel, again you will get R. Therefore, P equals to R. Similarly, Q. Already you know the Q. What is Q? 1 by 2 into A minus A transpose. This is Q. Already we proved. That equals to 1 by 2 into A. A means R plus S. Minus, here minus is there, minus A transpose. A transpose means R minus S. Here the bracket is very essential. Why? Because in front of there is a minus, therefore here bracket is very essential. That equals to 1 by 2 into, if you multiply r plus s, if you multiply with minus, minus into r, minus into minus plus s. Therefore, here r cancel, again you will get 1 by 2 into 2s. 2 to cancel, again you will get s. Therefore, finally what happened? P equals to r and q equals to s. So that means here a equals to p plus q. Here a equals to p plus q already we proved. If you take a equals to r plus s, if you take r equals to r plus s, then what happened? R equals to p and s equals to q, already we proved here. P equals to r and q equals to s. Therefore this sum is unique. So this is our required solution. Thank you, my dear students, all of you.